As I was telling Brittany here, I don't need my slides at all. Okay? Let's talk about syntax and semantics. Okay? The English language, like C++, has both syntax and semantics. The syntax of the English language is fairly straightforward and easy to understand. Similarly, the syntax of C++ is fairly easy to understand. So what are some of the things about the syntax of the English language that we are quite familiar with? Well, all sentences begin with a capital letter. Okay? All sentences end in some kind of punctuation. Most sentences have a verb, a noun. All right? Same thing with statements or commands that you're going to be given to the computer in the form of C++ code. The syntax requires that you are, first of all, it's case sensitive, which means there's a difference between the name C, lowercase c, A-T, and uppercase C-A-T. It's very case sensitive, so you need to spell things and be thoughtful of that process. The other parts of syntax are reserved words in C++, have specific meaning. So syntax has to do with the format of a statement. A statement can be written syntactically correct. And in fact, what our compiler does is the first thing it does is looks at the syntax of the code. So if you misspelled something, if you don't have punctuation, if you don't have something that's formatted correctly, it will give you an error message. So when you get that 0, 0, 0 error, 0 warnings out of the compilation process, all you have done is pass the syntax check of your code. So now the more difficult part comes in, and that is the semantic part of the code. Semantics means meaning. What does this mean? So when you test your program, you're testing its meaning. And as I was saying about the English language, we can speak very clearly in good sentences, but certainly say nothing. Okay? I can formulate good verbs and nouns and predicates and so forth, adjectives and adverbs, but you may not understand a bit about what I'm saying. And what I'm talking about here is the concept of ambiguity. When you and I speak to one another, there's a certain level of ambiguity that we can deal with. Our language, English language, is inherently ambiguous, which leads to a lot of arguments, understandings, and sometimes warfare and death. But we hopefully communicate very well. For example, if I say, oh dear, how many meanings can you derive from that statement? Well, it could be an affectionate term. It could be, oh, the building's getting ready to fall in. Or it could be, oh, there's a deer coming in. Okay. All right? But there's a lot of ambiguous terms that we have in our language. But in C++ and your source code, there can be no ambiguity. So there is no ambiguity allowed in the meaning of what you're trying to tell the computer what to do. So you must be rather specific, and close enough is not good enough. And I often say, you hear me talk about precision in engineering. We must be precise in what we do. And especially when it deals with computations. And we'll have some lectures later on in the semester where we'll talk about precision and number of decimal places in computations and doing things in a very precise way. I don't know, there was a good movie not too long ago about a group of guys that got together. They were disenchanted with their employer, and they decided to write a program that took all of the rounding percentages past 100th place, okay, and put that into a bank account. And the movie was funny because next day they had $300,000, and it wasn't supposed to happen that quickly. Well, it was not precise. Whatever the calculation they were trying to do to get that rounding area for their bank account was, pulling out some real money that they got. Did you see the movie? It was funny. It's not funny when a couple of years ago, the programmers of the AIDS testing device was imprecise in their measurements, and people got positive results when it should have been negative, and negative results when it should have been positive. You can imagine how funny that was. All right. You can also be aware that when bridges fall down because someone did not properly compute precisely the stress aspects of bridge construction, and people die, yeah, not very funny. What we do as engineers, and you may not think of this in information systems engineering, but it is very true. Sometimes you can deal with life and death situations like heart valves and medical equipment programming, and even sometimes the calculations that are taking place inside airplanes and automobiles. Okay? They're not precise, they can actually cause them suffering and death. So we have to be precise. So we'll talk a lot about that during the semester, but precision has to do with the concept of ambiguity. Okay? We need to be non-ambiguous. So the words we use need to be very precise. Now, there's a lot of aspects to that I'll talk about, and one of them is proper variable names. So in your assignment 2, which you'll be doing this week, you'll be asked to produce one or more, 4, I guess, in total variables. Don't make those variables A, B, C, D, and E, F, G. And make the total of those values something like this, total sum, something like that, so it's very clear and unambiguous to someone who's reading your program what you're talking about and what you mean. So variable names need to be fairly clear in their meaning. All right. But chapter 2 is not only about syntax and semantics, it's about the system development effort. Right. And we've spoken a number of times in the last 2 weeks about the process that we're describing here this semester is an engineering process. That's why we're an engineering student. We don't just write programs, we don't just construct buildings, or construct systems. We engineer them. And so the process is one that takes some painstaking planning and analyzing up front, so that when actually the construction takes place, or the programming or systems development takes place, it's a very smooth process. So, what is this process of engineering software? How do we execute an engineering project when it comes to software? Now, we talked about the phases of the system development life cycle, programming life cycle. We broke it down into 3 main phases. What do those phases mean? Let me go down into a little bit more detail about what's going on here. The word that best describes the engineering process is a waterfall model. The waterfall model. The waterfall is a good analogy for describing this, is because there's 2 aspects of the waterfall that are germane to this particular model. One is that a waterfall, things trickle down. And the process of engineering systems is a process where the output of one phase is the input to the next. And the output of that second phase is the input to the next. Another aspect of waterfalls that's appropriate here, by the way, Andy, are you filming this? Yeah. Great. Another aspect is that going back up the waterfall is very difficult. Very difficult. Once you're down at a certain point, going back up, you're going against the current. And the same thing is true about the engineering of software, engineering of systems. Once you've done your analysis of the problem and you've come up with a design, and construction or programming or systems development begins, and you find a problem, it's very difficult to go back to the design phase and redesign, but it's often very necessary. Very necessary. And once you design something, it's very difficult to go backwards into the analysis phase and to find out and analyze your problem. So as we navigate our way through this engineering process, we need to be rather thorough at each of those phases so that the need to go backwards, the need to redefine, redesign, reanalyze is minimal. But having done this for the better part of my life, I can tell you that any major systems engineering project has required backtracking of the waterfall model. Not only is it difficult in terms of time, it's expensive to do. Oftentimes, the process having been decomposed in such a way that we have separate phases, these phases are sometimes done by entirely different people. The programmers are not the ones that do the analysis. The designers are not the ones that do the programming. So they're passing their products on to other people, and that's where our products become very important in our waterfall model. Let's hope this works this time. So understand what I'm saying, and I want you to appreciate why you're here and not going to the Fry Institute or test college, whatever. Because what you are hopefully going to acquire here is a perspective that allows you not to be a simple builder, but a designer. Not to be a person do what again?
Click on the camera, the third one.
Right there?
Mm-hmm.
That one.
Mm-hmm. Now click on the board.
Okay, then what we're going to have to do is we're going to have to use that camera video with this and put them both out there. Okay. Working size. That better be.
And if it's just too big, you can always like cut it down to smaller sections. Make it simple.
Okay. I'll rely on your expertise. Help me with that. Okay. So now we're going to get to the boring part. Slides.
Killer, make sure you speak loud so they can hear you.
I thought I'm connected here.
Yeah, to hear. Come on for this one.
But I can take the audio off of here, right?
Yeah. I'm just saying just to make sure for this one.
All right, I'll try to speak louder. So, we know, having done our lab this past week, that there is one function that is always present in every C++ program. Anybody tell me what that function is? The main function. And you can imply by its word, the name, that it is the function that controls everything else. And so the execution sequence of the program begins the very first statement in main. But that execution sequence can be broken up by calls to sub-functions that we will talk about here in just a second. We'll take a look today at some of the constructs of the actual programs themselves. We'll look at legal C++ identifiers and how to name them, assigning values to variables, declaring name constants, string concatenation, output statements, and C++ comments. Can everybody see, or those in particular who have taken a look at assignment 2, where all of these topics here are called for? So let's move forward. We know that main function is the main function. This is illustration of the organization that you'll find in most programs. Now, here's the problem, and you'll see this as I illustrate this even more in more detail. The main function that I'm going to show you in this next piece of code I'm going to show you calls the square function and also calls the cube function, much like the decomposed party called the get place and by the food functions. Okay? So what the main function is doing is it's giving execution control to these particular functions. And I might note that it's not, these are very simple programs we're going to study for the next 14 weeks, but a more complex programming. Remember our parties of decomposition, where some things depended upon another. We had to find the place and the time before we could invite the people. And we had to invite the people to figure out how many people we had coming before we bought the food. But the record function could be done simultaneously with all this. You can find in actual programming there are functions that can be called sequentially or functions that can be called concurrent. In other words, this function can be running while I'm calling these other functions. So the same kind of organization that we saw in that first analogy with the party organization, we can also impart to our code design. But for the simple programs that we're going to give here now, you're going to give, the main function will give absolute execution control to a function, and only until when that function ends does the execution control return back to the main so other things can be done. So we won't see the simultaneous execution of functions. But let's take a look at this code. And I'm going to tell you that this is a very important code. I'm going to take the little time I have today to go through it so that you understand exactly what's happening. Because once you understand this concept of how functions are called and how execution control is given to these functions, and one little also aspect of this is parameter passing, you'll be 50% there as far as understanding this course. Okay? So let me wake everybody up. Wake everybody up. Everybody up. So that you get this over the next 10 minutes, it'll save you a lot of time and effort. So let's take a look at what's going on here. We see we have an include IO stream at the first line there, and that is a declarative statement that asks okay. Technical difficulties. First instruction is include IO stream, and this is a declarative that instructs the compiler, the program that you're going to use to translate your source code, to go and grab the code that's in a library called IO stream. Let's think of that as being another program that was written by somebody else. And it's actually what happens here is a copy and paste. That code from that library is actually pasted into the program at that point in time. But effectively what happens here is that now with that program that was written by somebody else, you have code that now understands cout over here on the side. You've probably used cout already. And you've probably already typed in IO stream and didn't know what it did. But that's going to be something that you'll probably type in every program that you'll write from this point forward, is include IO stream. Two strange statements here. Let me describe them in broad terms at first, and we'll get into more detail as the week proceeds. These are called function prototypes. Remember that word, prototype. We use it a lot. Prototypes are declarations of functions. It effectively tells the compiler that there are going to be two functions here called square and cube that are going to be defined later. In other words, it's telling the compiler that in main you're going to encounter two words, square and cube. And when you encounter them, you're not going to know what they mean, but know that they're going to be defined later. Okay? So I'm going to be very careful how I use these two words. Declare and define. The prototype declares it. And you'll see later on the next slide where they are defined. Like me telling you that, you're going to meet my cousin tomorrow. And that cousin will be defined to you later. Okay? And whatever reason you should be reading it will be defined to you later. But believe me, there's a need to declare your functions first before defining them. I'm not going to go into this using namespace until later, but we see our familiar int main. Okay? And inside our main function, the body, you'll notice there are 3 statements, 2 cout statements, and a return 0. The cout statement you've used before. It simply sends the output of what's inside those quotes to the control display, which is that black screen that comes up when you execute your program. What you may not be familiar with is this thing at the second line here. It says square, open paren, 27, close paren. That's called a function call. So here's how execution control works. It starts with the very first statement. It encounters a cout. It knows what cout means because it's been defined in the IOStream library. It looks at the operator, which is the 2 less than sign. It says, okay, cout is going to be taking this input stream. What is this input stream? Quoted the square of 27 is. And it's going to send out THE space SW out to the output stream and show it on the screen. Then it's going to stop. And it's going to give execution control to the square function. Let me just skip one slide ahead for a second. There's a square function. There's a square function. This is defined later in my code. We'll see what it means. It's obvious, but let's go back. You can imagine what it does. It takes the parameter 27. Yes, sir.
What do you mean by execution control? Like, what is?
Okay. Go back to our analogy of our party. We started the party process. Okay? Call my friend and say, look, find me a place. Okay? I can't do anything until you finish. So I just give an execution control for this party solution to you. You get your job done, take as long as you can, whatever it takes you, iterate around, call the places. When you got a place, you call me back. Give me that output. Once I get that output, now I've got control. I got information, I can control the party process from that point forward. Same thing happens in the computer. It's a step-by-step process. It's an algorithm that we're trying to implement. At certain points in an algorithm, the main controller has to stop working, give execution control to somebody else or something else, and then when that something else finishes, called my subfunction, finishes, then I got control again and I can continue on. It's that particular concept that I think is very important for you to understand. Because if you can, it's going to allow you to write programs of much complexity and make it even more complex. If I give execution control to a function, like in this particular case, I give execution control to a square function, the square function can call another function and give execution control to it. One thing being done in the computer one at a time. And when that thing finishes, it can give execution control back to square. Square can finish its job, then give execution control back to main. And we even get more complex here. Let me just throw this out for those computer scientists here. We'll study this next semester. There's an execution control sequence called recursion. Okay? Recursion is when you give execution control to a copy of yourself. And that's a function calling itself. That's a little more complex than what I get to you. Now, so what happens here is that square begins to operate. Square takes execution control. So, what does it use to begin its process? It takes on that parameter that's inside that parentheses. I'm going to use that word parameter a lot. That's a parameter. It's a value, 27, that gets sent to the square function. And you can see, and you'll learn if you read chapter 2 and a little bit of chapter 3, what that thing after square means. It says int n. It means that the thing that this square function uses for its input is an integer. So don't send me anything other than integers. The integer that's being sent on this particular call is 27. So n, the variable n, and I don't need to describe variables a lot, but I will on Wednesday in a little bit more detail. But we all understand what a variable is, right?
Yeah.
We use it in mathematics for years. A, B, C, A equals B plus C. What are A and B? Variables. They can take on values. So what the variable n has as its value now is 27. And you see the next statement, and the only statement in this function is return n times n. So what do you think happens there? It returns 27 times.
How does it know, like, what is the string? Because I remember we do that too. You have to let it know 27, it equals 27. So like,
Well, when the function call is made, it's 27 inside that parenthesis. So when the function header receives the 27, it puts 27 in the local variable called n. It's as if you said n equals 27. Yes?
Can you write a program after the return 0?
That will do what again? That will return 0?
After the return 0 line. Is this coming after it or before it?
After the rest of the the rest of the program coming after the return 0 or before.
You don't have to turn
That part right there is coming after.
Yeah, so like after that line.
After.
Okay.
The next question is after. When the program is completely finished, it will return 0. Well, that's not your question.
Like the rest of the program, that part where you have the int, square, int, and the next line.
Where is
It's
that?
part of.
That's
Is that before or after return 0? Because return 0 is the program.
Yeah.
Before.
Alright, but she don't see it before. That's what
no. Take a look. I'm answering your question. Take a look at this. That main at the top of my source code is where the return 0 is. That is a main function with a bracket at the end, and before the bracket is return 0. Right after that, in my source code, right after, is my square function. So even though I'm on 2 different slides, you can look as if I'm one page of information. Main, square, cube. Okay? I invite you to copy and paste this from the slides into a compiler and try to run it. It works. So, once square, yes, question?
One writing is called is coming in the address order.
Yes.
Integer square and integer. That comes after the initial function.
So it's all one program. It has 3 parts. Main, which I showed you on the previous slide, and then the second part of that same program is my functions after.
So you don't have to like put that in like random.
No.
so you can have this as a subprogram in the other.
It's in the same text file. It's in the same text file. I probably should break this up into one slide so you can see. It's one page of text. At the top is my main, next is my square, and next is my cube. Okay, we'll start back here on Wednesday. See y'all today.